minutes. So we're going to do the radical part of the 1.2. So let's just radicals. Now notice we're saying radicals instead of just square roots. You're probably used to just square roots. Radicals, of course, can be a square root, cube root, fourth root, etc. So if n is any positive integer, then the principal nth root is defined as the following. So, and you can see it's up there on the board, of course, too. So you probably have never seen this fourth root in front, this little tiny 4 here, little baby 4. That is the index on it, is what we call it. Now, the fourth root of 81 is 3, and here is why. If you make your old school factor tree, just to show you, you don't have to necessarily jot all this down. Well, I know it's like 9 times 9, 3 times 3. So here's why it is, of course, the final answer is 3. You have 4 threes. So 3 to the 4th is equivalent to 81. So when you have a 4th root, I am looking for a group of 4 same items. Now notice I said items because we're going to have variables too, not just numbers. If I have a 5th root, I'm going to look for a group of 5. If I have a square root, I look for a group of 2. Now, cube root of -8, if you factor tree this out, of course, we can do 2 times -4. So, of course, you can cube root a negative number, because -2 cubed, of course, is -8. I don't know why it's switching between black and red here, but there's the gist on that. Now, the other things, too, and I don't know if you, because I don't think you get into a lot of these radicals in honors geometry. Tell me if I'm wrong on that. But if you look in your calculator, if you look under the math menu, so it's got number 4, it will do the cube root for you. It's defaulted in there. So if I'm like, oh, I don't know, I can't remember the cube root of -8, you can punch it in. So let's quit out of this. And I just type in my -8, and there it is. Now, if you wanted to do that 4th root of 81, you can do it. Anything higher than a cube root, you have to tell your calculator the index. So I'm going to hit 4, math menu, number 5 this time, and that pops it on as the index, and then we had 81. So I didn't know if you knew where those other higher roots were in your calculator, under the math menu, just for the record. Let's clear all of that. Okay, let's get into it here. So these are all on your notes. There's nothing for you to fill in, but we do need to talk about these properties here for a second. Most of them you're going to see obviously today. So notice, of course, when you do all these crazy roots, that's a little tiny product. Oh man, I really butchered writing over that. But anyway, that's product between it. So when you have multiplication underneath, you can think of it also as doing the root of each number individually. So it just depends on the values. Sometimes I multiply them together and then I'll root it because that's simpler. Sometimes I root each number individually. It just depends what they give you. If you have a root over a whole fraction, rooting the top, rooting the bottom. Okay. This looks crazy. A double root, we call it, number 3. So of course you can see you can make it a single root. Just multiply your indexes together. So if you had a cube root and a square root, really the 6th root. Make it easy on yourself. The root and the power, of course, cancel out. We're going to talk about that absolute value in a second. And you can see the same thing here. Now, we saw back on our, I still have them up here, these true-false questions back to the beginning. Here to find it, this guy. Probably a lot of us thought that was true, but then I said, well, if you put a negative number in there, like -3 squared, square root of 9, you're going to get 3. They're not the same thing. So that's where that absolute value, little nitpicky rule is going to come into play here today to help our cause. All right, simplify. Here we go. So cube root x to the 4th. So the index is the key, cube root. So in my head right now, I'm like, okay, groups of 3, groups of 3. Now, once you catch on to this, you're going to do these with way less writing than what I'm going to do here. But for dramatic emphasis, thinking about my groups of 3. So I'm going to rewrite x to the 4th. I'm going to be dramatic about it. I know it's the same thing as x cubed times x. So the reason I expanded it that way instead of maybe say x squared, is I'm looking for that group of 3. Now my cube root and cubing cancel out. So that's just going to stay. And then this poor guy is still under the cube root. Now, do I really need the x to the 1st on that? No, I'm just going to rewrite it nice and pretty x. It is a cube root in odd index. I don't have to worry about absolute value because you can cube root negative numbers. I'm just going to write this prettier. Now, to me, I think that's a lot of work for something I think we could probably have done in our head and go straight to the answer. So I just think about how many groups of 3 can I make out of 4? Well, I can make one group of 3, and I'd have a remainder of 1 underneath. So that's how I approach it. How many groups can I make? That value goes outside, the remainder inside. Let's practice some more. All right, we already know the 4 through to 81. We did it earlier. We know that that's 3. So the question is, how many groups of 8 can you make out of 4? How many groups of 4 can you make from 8? 2. No remainder. How many groups of 4 can you make from 4? 1. No remainder. Now, you don't need the 1 on, that's for drama, okay? No remainder, so I don't have any 4th. I'm not going to write the 4 through to 0. That just seems worthless. But I am going to do one other fancy thing. Since it's a 4th root, of course, we can't do the 4th root of a negative number. So remember, the even indexes, your 4th root, 6th root, etc., for a little insurance policy is where I'm going to slap some absolute value on it. Around the variables to ensure they come out positive. Now, if you really are intuitive, I would totally take this answer. But if you're super intuitive, which I know some of you are, if you square a number, will it ever come out negative? No. So I could have just put the absolute value on the y. Is it wrong if you put it on both? No. But the squared will always come out positive, so I'm not really going to worry about it. So it's just one little dicey thing we got to be conscientious of. Okay, we're going to add some roots. So in order to add radicals, you do this back in Algebra 1, but it's been a while. They have to be what we call like radicals, meaning you cannot add a square root of 32 and 200. I need the same value underneath the radical, like a square root of 5. So we're going to simplify these. Now, lots of ways to simplify. Because we have the higher indices, I'm going to go old school factor tree. So I know 32, break it down however you want. I'm going to go 2 and 16. And then, of course, 16 I can break down. Now, I know, like the 4s, we could all break them down, of course, more. And we're welcome to do that. But I'm like, wait a minute. Don't I already have a group of 2 in my factor tree? That pair of 4s. So whatever you have a group of 2 of, that's going to go outside. And then, of course, my single number stays inside. Let's do 200. So I'm going to do, I don't know, let's do 2 times 100. Now, lots of ways to break down 100. I could do, 25 and 4. I could do all sorts of things, but I'm trying to work smarter, not harder here. 100 is a perfect square. I would go 10 times 10. Yes, I know you can break the 10s down further, but bam, I got a pair of numbers. I'm always looking for a pair. The pair goes out front. The single stays underneath. I'm like, oh yeah, those are like radicals. Let's add them together. 4 square roots of 2, 10 square roots of 2. We have a total of 14 square roots of 2. All right, D. Everybody thinks D looks super duper easy, and it kind of is, kind of is, but there's a little twist to it. Remember in your properties, if we go back here a couple slides, we can only, I'm thinking about the top one here, because at first I was like, oh, I'm just going to square root those 49s, and I'm going to make it easy. I'm like, oh, crud. That only works where you can square root, apply the root to everything if you have product or quotient. So 1 and 2, not addition. So I'm like, okay, all right, we got to get a little twist here. Well, just when you least expect it, that's throughout the whole year, you can factor. So I'm like, okay, all right, I got a lot of 49s here. I'm going to factor a 49 out. The reason why, now I do have, for dramatic emphasis, product. I can apply the root to both terms of my product, meaning I can square root 49. Got it. Now, this is addition. I unfortunately cannot apply my square root to both, so I'm just going to leave x squared plus 1 underneath. You can only apply the radical on product and quotient. It's one of those nitpicky rules, they're not equivalent. All right, more of the same, but fraction exponents, rational exponents, all that sort of good stuff. Now, reason we practiced all those fraction or rational exponents Friday is because they're also radicals really in disguise. So rational, fancy name of course for fraction. I like to say rational usually, but sometimes I'll throw fraction in there. I'm going to put the 1 on here for dramatic emphasis. So if you have a rational exponent, the numerator is the power, the denominator is what style of root. So same thing here. The numerator is the power, denominator on the fraction is the root. So the denominator of the fraction and the exponent, that becomes the index, we call that. What type of root? 4th root, 5th root, etc. And the numerator becomes the power. So you probably have never seen that before. I don't think that's something they get into in Algebra 1 back in the day. All right, let's flip the page and do some of these. Not a lot on here because then we're going to practice. Whew! Simplify without a calculator. Oh boy. Okay. Could you punch this in your calculator exactly how it appears and punch it in? I mean, yeah, sure, okay. But we should be able to do it without our calculators. So always, here's my pro tip. You'll hear me say it a lot in this class. Try to always rewrite the numbers in terms of a smaller number. Like I'm looking at 4 and I'm like, it's 2 squared. We know 4 is 2 squared. We got it. And we're still to that 1/2. And I'm like, oh, well that's not so bad. We know our power properties. Exponent raised to an exponent multiplying. What's 2 times 1/2? 1. So we have 2 to the first, aka 2. Now, the other way to kind of think about it too is, remember we just talked about these rational exponents. This is the same thing, square too. Square root of 4 to the first. We know the square root of 4 is 2. Okay. All right, let's do B. So again, I'm like 8. I can make that a smaller number, 2 cubed. To the 2/3. I'm like, oh, great. Power to power. So I'm left with 2 squared. We all know 2 squared. Now, the other way, because always there's more than one right way to do these, you can think about this in radical style. That's the same thing as the cube root of 8 squared, or the cube root of 64. You might have known the cube root of 64 is 4. Maybe, maybe not. Do I care how you come up with the 4? No, just that you can come up with the 4, okay? All right, 125, I just happen to know that that is 5 cubed. I'm sure you did too. Then of course, power to power, those 3's are gonna cancel. And we know we never leave an answer with a negative exponent. So what fine fraction is the final answer? Final answer is 1/5. So this is, you gotta be good at fractions, you gotta kind of have a good number sense, etc. All right, those are too easy with just some plain numbers in them. Let's do some variables. Same principle. Okay, simplified by writing radicals is rational exponents. Now remember, rational exponent, fancy name for fractions. I'm like, okay, I can do that. So instead of making that the cube root of x to the 4th, I'm going to put it 4/3 power. Now, not a lot of simplifying we could really do on that. The only other thing right now we could do, but I don't like it, is if you move it to the top so you get it out of fraction style, what's the sign on your exponent? Which we never want to leave it with a negative exponent. So that's as far as that one's going to go for right now. Simplify, write it, rational exponent, I did it. Okay, let's try this guy. Square root of x, I'm going to make that x to the 1/2. Because remember, the square root, you don't have the 2 on the radical, you just know that the square root is a 2. 3. Same thing, I make this 1/3. Remember, your powers are 1 on those. All right, so let's see. I think we can clean that up a little bit. I'm going to do 2 times 3. And we know from our exponent properties, when you multiply, you add the exponents. What's 1/2 plus 1/3? 5/6, I heard it. Got it. So all the exponent rules, all the fraction in 1. Okay, this looks weird, I know. Okay, but remember, just to flash it back so you know we're referencing. One more. number 3. When you have a radical of a radical, you can clean it up and put it as a single radical. You just multiply the indexes together. Gotta go further. One more. Okay, so what's the square root, square root? Think about that. Now, notice, okay, let's kind of break it up here a little bit. I'm going to leave the x here. I'm going to leave this now as to the 1/2. So I simplified that down. And then we have both of this, all of this underneath to the large square root. So you have some choices here. We could apply the 1/2 to everything. We could clean the stuff up inside and apply that to the 1/2. Doesn't matter, we're going to get the same thing. I'm just going to put the 1 on there for dramatic emphasis. I'm going to go ahead and add those up. 1 plus 1/2, 1 1/2 for 3/2. And then I'm going to multiply those together. 3/2 times 1/2, 3/4. So I knew it was going to turn into a 4th root, square root, 4th root. But the little tricky part was, unfortunately, that first x was only under a single radical, not the double. So many properties. God, I love this stuff. Okay, last thing I'm going to show you, then we're going to practice how to rationalize the denominator. I'm sure you've heard that. You never leave a radical, you're probably used to square roots, a radical in the denominator of a fraction. So we're trying to figure out what to multiply by to turn it into a whole number. When we do this, we're not changing the value of the fraction, just the looks of it. 2/4, 1/2, 4/8, 3/6, it's all half. They just look different. So that's what we're going to do here. Now, I gave you an easy one to start with. I know you get into this stuff in geometry when you do all your SOHCAHTOA, opposite over hypotenuse, all that good stuff, and you can't have the radical at the bottom. Nice and easy. Square root, square 2, group of 2. I'm going to put one more square root of 3 on. But of course, I'm going to balance my fraction. Whatever you put in the bottom, we're going to put in the top. So I've got 2 square roots of 3 up top. You're probably going to skip this step. Square root of 9 on the bottom. And we all know the square root of 9 is just 3. But you probably went straight to the answer. So equivalent values, if you punch the original problem in your calculator in our new answer, you'll get the same decimal. They're just in a different style. No radical on the bottom. All right, that was an easy one. Well, this one's easy too. Now, cube root though. Probably haven't done a cube root. So for dramatic emphasis, that's 5 to the 1st, of course, down there. Cube root. I need groups of 3. So I am going to rationalize it like the last one, but I got to get smart here. If I just do a cube root of 5, like how I just did the square root of 3 back here, you're not going to have your group of 3. We're going to have 2 5s. Well, I need 3 5s. So I'm going to make it squared, or 25, I guess, if you wanted to. And of course, I'm going to balance the top of that. So I have 1, I'm not writing the 1, cube root of 5 squared. Let's make just that cube root of 25. You will probably skip this step, but I'm going to put it on your notes for dramatic emphasis. And the denominator, we have 1 5, 2 5, okay, cube root of 5 cubed. And of course, the cube root and cubing cancel. And again, I probably always have more work than you guys will have on the homework, this intermediate stuff. Totally fine, not to show all that crazy stuff. All right, 7th root of 1 over a squared. Well, 7, oh man. 7th root of 1. Well, any root of 1 is just 1, so I'm just going to make that easy on myself. So I'm going to root the top, root the bottom. So 7th root a squared. Okay. So now I'm going to rationalize it because I don't want to have that 7th root in the denominator. So again, we're going to work smart here. I've got 2 a's. I need a group of 7. I'm going to have to put 5 more on it. So a to the 5th. Same thing on the top, 7th root, a to the 5th. So the top, 7th root, a to the 5th. In the bottom, now let's skip the intermediate step. You have your 7 a's, a to the 7th was going to cancel with your 7th root. So many good little tricky rules. I love it. What questions can I answer for you on those last 3? So like I said, I could stand up here and do a bazillion examples all day long. I don't know if you'd like that, really.